Okay, so now that we have found the velocity, or sorry, the acceleration of the runner, let's figure out how fast they're going. Now, there's a couple different ways you could do this. Some people actually went through and said, what if I don't know the acceleration? Is there a way to figure that out? And so you can think about which of your equations leaves out acceleration. But I think it's honestly easier to use one of your equations that's even on your equation sheet, because now we have the acceleration from above. So after those 2 seconds, what do we have? We've got our final velocity is equal to 5 meters per second squared times 2 seconds. So our final velocity is 10 meters per second. When I think about the time needed to run the full 100 meters, why it says total is that I have the beginning part from part A, the time from part A of this problem, plus the time for the rest of the 90 meters. That's going to be the total time. So I already know there's 2 seconds that part A and B are about. I need to find what's the rest of the time for the 90 meters here. So if I know, even easier, now I know that my final velocity is a constant, that my acceleration is 0. This runner cannot run any faster. So that means that I can, for the remaining 90 meters, use our very basic definition that change in position divided by time is equal to velocity. And I want to solve for time. So time in this case is equal to my displacement divided by my velocity, which is going to be 90 meters divided by 10. Whoop, off the screen, apologies. So that's going to be 9 seconds, but I need my total time. So I've got 2 seconds plus 9 seconds equals 11 seconds total. All right. If I was going to put that on a graph, the graph is difficult to show because there really is only acceleration for those first 2 seconds up to 10 meters away. So I should have a curving line, right, up to that point, and then I reach the 100 meter mark 11 seconds later. So there's the rest of my line. So I have a little bit of a curve down here where I'm accelerating. And then while I'm running at a constant speed, it should be linear because that's a constant velocity. All right. And then my very last question here. Bicyclist moves up a hill. Before I even read the rest of the problem, I'm going to look at my graph and see what does it say. It says that I'm starting at a big velocity here, and as time goes by, my velocity is getting lower, 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 lower. So this does mean that I'm slowing down. So if you decided to coast up a hill, so coasting means that you stop adding any energy, you're going to let just nature carry you forward. Your own momentum, I'm sure is what the dictionary says, but we haven't technically defined that yet, so I don't want to use that word wantonly. But I'm going to run into a hill, and then as I go up, gravity is going to accelerate me downward, which means that my velocity will decrease. So this graph is correct. So, and the reason is because the bicycle will decelerate because of gravity. As it goes up the hill. And that our slope is what tells us that there is a constant negative acceleration. So those are the solutions for the written part. Please check back at the next video for the solutions to the multiple choice.